Here's an example. Let's say you have a hydrogen atom and you have an electron in the 2p orbital. Because of spin-orbit interaction, okay, normally those 2p orbitals are degenerate, right? Six-fold degenerate. What are the 6 possible ways that an electron can be in a 2p orbital? It can be 2p, 0, m can be +1, 0, or -1, right? That's your possible m values, and it can either be spin up or spin down. So there's 6 possible ways. So we say that the 2p orbital or the 2p sublevel of hydrogen is 6-fold degenerate. But because of spin-orbit interaction, what actually happens is that that 2p sublevel, okay, under very high resolution, if you have a very sensitive instrument, you can actually see that there's actually 2 levels there. Okay, we refer to those levels as doublet p1/2 and doublet p3/2. Okay, and we'll learn to determine these when we look at a more general case of you have more than 1 electron in an atom. But for now, the way you interpret this is this p right here. Okay, capital P. That's for that means that the quantum number for the total orbital angular momentum is 1. That's the code for L = 1. Okay, in other words, if I were to ask you what is L squared of the psi for a doublet P1, doublet P1/2, what would be the eigenvalue for that? L squared. And that's going to be L times L + 1 h bar squared psi of doublet P1/2. Okay? So that letter P, capital P, okay, small letter p is for 1 electron. Capital P is the total, which in this case is also for 1 electron. Okay, but when we get to atoms with more than 1 electron, you have to use the capital letters for the total orbital angular momentum. Okay, now the 1/2 and the 3/2 label here, okay, that's the total J. That's a quantum number for the total angular momentum, spin and orbital angular momentum. So J equals 1/2 and J equals 3/2. Okay, those are the allowed values of the quantum number J for the total orbital and spin angular momentum. Okay, so for example, if I were to say J squared psi for the doublet P3/2, what would be your eigenvalues? It's going to be J times J + 1 h bar squared. What's our J in this case? 3/2 times 3/2 + 1 and h bar squared right there. Okay? So that subscript there in that label for the state, name for the quantum state is the J. So this is, P here is the code for L, and the 1/2 is the code for J. The 2 over here on the left-hand side as a superscript, that's the value of 2s + 1. Okay? We can say that what we have here is a doublet. You can think of them as also known as the multiplicity. Okay? So 2s + 1 is the multiplicity. Let me clear this out. Okay. That 2 right there, that's called the multiplicity. So we say the multiplicity here is equal to 2s + 1, and that's equal to 2. Okay? S here is the quantum number for the total spin angular momentum. Okay? So what's the total spin angular momentum for 1 electron? What's the quantum number S? 1/2. What's 2 times 1/2 + 1? 2. Okay, so multiplicity, one way you can define multiplicity is to say that's the degeneracy because of spin. Okay, because if S is 1/2, then M sub S can be either plus 1/2 or negative 1/2, right? So there's two ways that your spin, total spin angular momentum can be oriented. It's either spin up or spin down since we only have one electron. So we say our multiplicity is 2. Okay, so anytime you have a system, you have an atom that has one unpaired electron, okay, immediately you can say that the multiplicity of the quantum states there is 2. The degeneracy that we can attribute to the possible orientations of the spin momentum, spin angular momentum is 2. It's either spin up or spin down. Okay, so this expression right here, the doublet P, is called a term symbol. And when we get to atoms with more than one electron, we're going to look at a more general way of deriving that term symbol. So a term symbol tells you what the multiplicity is. In other words, it tells you what the quantum number S is, right? Quantum number S, and it tells you what the quantum number L is. So you use a code letter for quantum number L. When L equals 0, you have what's called an S state. Okay. When L equals 1, you have what's called a P state. When L equals 2, you have a D state. So it follows the same pattern. For one electron, you use lowercase s, p, d. And for if you're dealing with the total angular momentum, you use capital letters. Okay. And your S here is the spin quantum number, total spin angular momentum. Right. So doublet P, you read this as doublet P. That's the term symbol. Okay. So what happens is this: because of spin orbit interaction, okay, what actually happens is your doublet P, your 2p configuration. Okay. We said, having one electron in a 2p subshell, there are how many ways that can happen? What's the degeneracy? 6. 1, 2, 3, 4, 5, 6, right? Well, that is going to split into 2 levels. Okay, the lower level will have 2 states. This is called the doublet P 1/2, and it turns out that the higher level in this case would be your doublet P 3/2. Okay, 4 quantum states. So there's still going to be 6 states, but 2 of those states would actually be lower in energy than the other 4. And how do we distinguish between these 2 quantum states for doublet P 1/2? This is J equals 1/2, right? Well, they differ in their M sub J's. Okay, so M sub J would be plus 1/2 or negative 1/2. Remember, for a given J, your M sub J can go from J to negative J. Okay. So for J equals 3/2, these 4 quantum states correspond to what M sub J values? 3/2, 1/2, negative 1/2, and negative 3/2. Okay? Now, if you have an electron in a 1s orbital, there is no spin-orbit interaction. Why is that? What's the orbital angular momentum for an electron in a 1s orbital? There's no orbital angular momentum, so there's no spin-orbit coupling there. Okay? And like I said, the evidence for that is in the spectrum. Let's see, I have the link right here. Let me see. Hydrogen fine structure. Let me see if I can look that up. Just do a search for hyperphysics. Spin orbit interaction. And you'll see the hydrogen fine structure. So this is the site at Georgia State University. So this is what happens. So you have an electron in a 2p orbital. Okay. In the case of hydrogen, it splits into a doublet P 1/2 and a doublet P 3/2. Okay. And that's Instead of seeing just one line in the spectrum, you see two. And the splitting of the line is about 4.5 times 10 to the negative fifth electron volt.